All right, I'm finishing out this last bit of problem. Sorry, if I go over 15 minutes, I gotta break it up and resave. It takes forever. So our acceleration is our first derivative of velocity at pi over 4. And so here's a velocity function. When you take the derivative of this, that's going to be negative 10. Derivative sine is cosine. T plus pi over 4 times the derivative of this, which is just 1. We want to do this at pi over 4. So that means we'll have pi over 4 and pi over 4 is pi over 2. Cosine of pi over 2 is 0. So this very swiftly goes to 0. That's our acceleration. Maybe I could have gotten that in 12 seconds, but who knows. Anyway, that's our acceleration at pi over 4. $71. All right, number 71. Vertical motion. On Earth, if you shoot a paperclip 64 feet straight up into the air with a rubber band, the paperclip will be S of t equals 64 t minus 16 t squared feet above your hand at t seconds after firing. Find d s dt and d squared s dt. That's the one. D s dt is the first derivative with respect to t. So that's going to be 64 minus 32t. Second derivative with respect to t is going to be minus 32. So there's our velocity and acceleration, we assume. How long does it take the paperclip to reach its maximum height? Its maximum height. So that's going to go all the way up. It's going to stop. It's going to come all the way down. So that occurs when our velocity is 0, because we're changing direction, right? Goes up, stop, come down. So we'll set this equal to 0. And so that means that 64 equals 32t, and t equals 2. So that's when the paperclip reaches its maximum height. With what velocity does it leave your hand? Well, that occurs, our velocity at time 0. So that means that t equals 0. So that means that'd be 64. Oh, is that given in feet per second? Yeah. 64 feet per second. On the moon, the same force will send the paperclip to a height of 64t minus 2.6 t squared feet in t seconds. How long will it take the paperclip to reach its maximum height, and how high will it go? All right. Let's see. So these ones don't work anymore. So the same force that means our initial velocity is the same. We're looking at our position on the moon is equal to 64t minus 2.6 t squared. Keep a second. Maximum height and how high will it go? All right, so we got new position function. So our velocity on the moon, t is given by the first derivative of this, which is 64 minus 5.2t, and our acceleration on the move equals negative 5.2 t. It asks how long will it take the paperclip to reach its maximum height. So when our velocity equals 0 again, that means 64 equals 5.2 t. Divide by 5.2. Divide by 5.2. 64 over 5.2 equals t. We have to figure out what that is later. But somewhere around 10, 11, 12. Oh, we'll just do it out. We have time? Yeah, 6 minutes. All right, so 64 divided by 5.2. 5.61. 5 goes into 12.2. 5 goes into 16.3. 0. So approximately 12.3 seconds in. And how high will it go? So there's our original height position function, into which we need to set this. So our new height at 12.3 seconds will be 64 times 12.3 minus 2.6 and 12.3 squared, which we'll assume the book is right. Where did they put the answer? 393.8 feet. I think that'll work. Number 72, almost done. Thank goodness. These last problems are exactly what the AP is like, so they're important. Are important. This is gonna save you a couple $100 come college time, assuming you only take calculus, or you don't have to take calculus instead of taking it several times. 71 or 2. We're in free fall. Two balls are falling from rest at a certain height in centimeters above the ground. Use the equation S equals 490t squared to answer the following questions. All right, so our position, given by that. How long does it take the balls to fall the first 160 centimeters? What is their average velocity for the period? All right, how long does it take them to fall the first 160 centimeters? So what we're doing is at -1, going to be 160, from a certain height above the ground. Let's see here. Now, I guess they're saying this is our displacement. Yeah, take displacement as S. All right, so 160 equals 490 t squared, means 160 over 490 equals t squared. Because that cancels, that means that t equals square root of 16 over the square root of 49, which equals 4/7 of a second. What is their average velocity for the period? If they go from, so here's our time, here's our displacement. So at time 0, we're at 0. And at time 4/7, we're at 160. So our average velocity is going to be our total displacement over our total time, which is just 160 over 4/7, which is 160 times 7 over 4, which is 280 centimeters per second. How fast are the balls falling when they reach the 160 centimeter mark? What is their acceleration then? So here we go, part B. How fast are they going? So we want our instantaneous velocity at time equals 4/7. So our velocity at a given time is equal to the first derivative of our position. And that's going to be 2 times 490, which is 980 t. And so our velocity at time 4/7 is 980 times 4/7. And 7 goes into 980. That cancels. That's going to be 1 with 28, 4, 0, 14, 4, 52, 56. So our instantaneous velocity is at 560 centimeters per second. And our acceleration at that point, our acceleration will be constant because our velocity is 980 times t, and our acceleration is our first derivative of velocity. And so that's derivative of 980t is just 980. So that's 980 centimeters per second squared.